Okay, well, we've been talking about steels. Now I really want to get into the weldability of the steels. But just to remind you what we learned about the steels, by the way, I finally figured out how to fix the brightness on this thing. If we look at cooling of steels, we find that depending on the cooling rate, A, B, C, or D, and the time in seconds versus temperature, you might form martensite, austenite, ferrite, pearlite, bainite, which have these different time temperature profiles. This is a continuous cooling transformation diagram, a CCT diagram. It turns out the transformation from austenite to ferrite, from austenite to pearlite, from austenite to bainite, these are all diffusion controlled transformations, which is what most of you know about phase transformation. Some atom has to diffuse through the crystal, and it takes some time to do that. It turns out the austenite to martensite's somewhat unusual type of transformation. It doesn't just occur in iron carbon alloys, it occurs in nickel titanium alloys, some copper-based systems, a number of different systems have martensitic phase transformations. The martensitic phase transformation is basically just a shearing or displacement of the crystal lattice. So it goes from one structure to another. And that means it occurs at something close to the speed of sound. Now the speed of sound is something on the order of 5,000 meters per second in a solid. And so the time for the austenite to martensite transformation to occur is something on the order of, let's say, 10 to the minus 10 seconds. Okay, it doesn't take long. There's no diffusion of atoms that has to occur. It's just a shearing of the lattice, and that means you will always get martensite. If you don't get one of these others, if you can beat the nose of the C curve, like this A, you will get martensite. Martensite is extremely hard, brittle unless it's been tempered to allow some of the carbon to diffuse around and relieve some of the strains that are imposed on the lattice. So you don't want to get untempered martensite. You do want to get something that's hard. You sometimes like to get bainite, but you're going to get a transformation when you weld, okay, in the steel, and that transformation can lead to excellent weld matching, so you can get same strength as the base material. You can't always get that in, say, some of the aluminum alloys, but systems that are that have a change in crystal structure from one crystal structure to another, such as the iron-based systems or the titanium-based systems, you can usually get matching strength between the weld metal and the base material. And so that's one of the advantages, an advantage that the iron-based system has. Now, I've told you that the problem, the Achilles heel of steels in terms of welding, is hydrogen. And what can happen is you'll get cracking. Okay, here's a picture of a hydrogen-induced crack in a weld. Typically they start at the toe of the weld, or it's sometimes down towards the bottom in the root of the weld, basically at stress concentrations. And there is a residual stress pattern here. You don't get cracks unless you have stresses, but just from the fact that the fusion weld is made by having localized heating, you're going to get localized stresses. The localized heating produces, on cooling, due to the thermal expansion differences, produces the residual stresses, and those residual stresses can result in cracking. Now, I'll give you another example. If there's something as innocent, let's say, as an arc strike is just something where someone hits the arc against the steel somewhere where they didn't intend. These are stray arcs. It's not in the weld zone, but the guy's got his helmet on. He can't see through it unless the arc is giving a lot of light. And if he accidentally hits the steel somewhere, you'll get a little arc strike. Okay, that's what an arc strike might look like at higher magnifications in some steels. Here's an arc strike with little cracks growing from the edge. You end up with tensile residual stresses right around the outside heat affected zone. The fusion zone was molten, and it doesn't have as high as stresses, but the get a very high concentration of thermal stresses during cooling, and you'll get cracks radiating from that little arc strike. So arc strikes they may be cosmetically unappealing, but they can actually be harmful, and so many of the codes will require that you grind off the arc strikes, okay? And you don't like welders who go around hitting the electrode where they're not supposed to when the lights aren't on, okay? When the arc's not going, so far as that goes. Okay, hydrogen cracking has many names. It can be called hydrogen cracking. Sometimes people confuse hydrogen embrittlement with hydrogen cracking. Hydrogen embrittlement is the fact that hydrogen in the steel can cause the steel to act in a brittle manner. Hydrogen cracking is the actual production of a crack, okay, due to the hydrogen embrittlement and an applied stress. So one thing that's worthwhile thinking of, there's what we call a Venn diagram that relates to hydrogen embrittlement. And so if I think of stress as one of the components that are necessary to form a crack, if I think of hardness, the higher the hardness of the steel, the greater the tendency to cracking, and finally the amount of hydrogen that's present, these three combine to give me cracking. And so if I have enough of all three, the reason we like a Venn diagram is the circles can expand or contract. And if I have all three of them in sufficient quantity, I'll get cracking here in the intersection zone. If I can reduce the stress, or reduce the hydrogen, or reduce the hardness, I can get rid of my overlap zone in the center where all three of them come together. And therefore, I don't get cracking. So there's three things I can do to prevent hydrogen cracking. Reduce stress, reduce hydrogen, or reduce the hardness, so far as that goes. There is I was looking online this morning, there's actually a couple of nice videos that my secretary will send you a link to. I didn't find the one I was interested in, okay, but I did find two others, one older and one younger. It turns out sometime back in the 1970s, some people at Rensselaer Polytechnic took a piece of steel which they polished, and they had it so they could stress it, and they had a crack in it, and they immersed it in water and put it in a microscope, and they looked at just the cracked tip, and they could see bubbles coming out. As they increased the stress, they would see the hydrogen bubbles come out with greater frequency right at the cracked tip. Why is that? Well, hydrogen is an interstitial atom. It likes to strain the lattice. And if you strain the lattice, the hydrogen will go to the lowest energy state where the lattice is already expanded. That's at the cracked tip, okay? I'm pulling on the lattice at the cracked tip. And so if the hydrogen was uniformly distributed within the steel, such as my can of Sprite with the CO2, before I opened it up, if I now I have it in a solid, not a liquid, but if I take that hydrogen with that steel with hydrogen everywhere, and I apply a stress and I have any kind of discontinuity, the hydrogen will migrate to the cracked tip. Now it's a diffusion process and it takes some time. How much time it takes depends on how much hydrogen is present, the thickness of the steel, and a number of other things. But unfortunately for us, in the world we live in, the rate that hydrogen diffuses and can cause cracking happens to be greatest or lowest on this diagram. Let me go up a little bit. If I take a notched specimen like this and I apply a stress and I look at different temperatures and I have a hydrogen-free specimen, this is strength, megapascals, yield strength. I'll give you some numbers on another graph. And I look at hydrogen-containing specimens, right around room temperature is where I get the fastest cracking, okay? Or the cracking at the lowest stress. And the reason for that is at temperatures below room temperature, the hydrogen can't diffuse. At temperatures above room temperature, the hydrogen can diffuse fairly rapidly and will come out of the steel. It'll just diffuse out. And so if we heat up the steel, we can get rid of the hydrogen. We can reduce the size of this circle over here, the H2 circle, is one way to prevent the cracking. To put it in more concrete terms, this actually comes from sulfide stress cracking in a high-strength low-alloy steel. This is hydrogen sulfide, sulfide stress corrosion cracking. Turns out sulfide stress corrosion cracking is merely another form of hydrogen cracking, but it occurs when you have H2S gas around, which you just soon not be around because it's actually toxic gas, and you can suffocate or you can die from breathing too much H2S. Anyway, this is time to failure versus temperature. At 25 degrees C, which is room temperature, we have cracking in less than 2 hours. If we cool down, it takes up to 20 hours because the hydrogen can't diffuse to the crack tip. Yep. I'm going to talk about that in a little bit. Just hold that. If I don't get to it, remind me, okay? Here, at higher temperatures, I can diffuse the hydrogen out before it can all congregate here to do its damage, okay, at the crack tip. So this quantifies it. I've been telling you that hydrogen cracking, you have to do something about getting rid of the hydrogen within about an hour to 4 hours. And this quantifies, at least for hydrogen stress corrosion cracking, but we know it for other things, that you've got to get rid of the hydrogen fairly quickly. But because hydrogen takes time to diffuse to the crack, you have time to heat the steel up and get the hydrogen out. And that's why if I electroplate, we talked about electroplating of bicycle tubes, if they had plated the bicycle tube and gotten it into a 375 degree Fahrenheit furnace, which is the standard temperature, within an hour, they wouldn't have formed a crack. And the bicyclist wouldn't have become a paraplegic. You formed a crack, and a fatigue crack grew from that. It turns out if I go to one of the welding codes, and I'm talking high-strength steels for bridges, this code requires that you not test for cracks in your welds until 48 hours after you've made the weld. Why? Because if you test within the first hour, you might find no crack. And a couple hours later, there might be a crack. And you just missed it because you tested too quickly. You have to sit for 48 hours before you can do your non-destructive testing if you're building a bridge or a building out of 100 KSI steel. The U.S. Navy building nuclear submarines, that's HY-80. That's a weld that's about 1 inch thick. It's got a backing bar so the metal doesn't slip through. It's got a heat affected zone. This thing was probably made back in the 1980s, okay, but I coated it so it wouldn't rust. But basically, the cracks would form in the heat affected zone if you didn't do something about it. This is a typical diagram of weld cracking, toe cracks, root cracks, underbead cracks. These are all hydrogen cracks that form during welding, but not right away. We often call this delayed cracking. It's hydrogen cracking. It's also called delayed cracking. It's sometimes called underbead cracking. It's got 5 or 6 different names because lots of people have seen it lots of times. It still occurs frequently, okay? I get several hydrogen cracking problems thrown at me each year because we know about it, we know how to control it, but that doesn't mean that people do. Now, where does the hydrogen come from? What's the largest source of hydrogen in the world? Water, the ocean, okay? It doesn't come from the ocean, but it does come from moisture, because moisture's everywhere too. So it turns out One of the key areas is moisture. What also contains hydrogen? Hydrocarbons contain hydrogen, right? So any grease or oil that's around, lubricants. I can tell you a story about welding of the Seawolf submarine, and I tracked it down, in my opinion, to lubricants. The moisture can even be humidity in the air. Okay, so one of the common things, and we'll talk about it some more, are stick electrode coatings. Okay, so stick electrodes are still used. Back 40 years ago, 60% of all welding was done with a stick electrode. You take an electrical copper clamp, you clamp the electrode on this end where it has no flux coating, which will melt off and form a slag to pull out the impurities and protect the weld. It has a tip that's been brushed off so that you can strike an arc if you have a helmet on, hopefully, so you don't sunburn your eyes. Okay, the light intensity coming from the electric arc will give you a sunburned retina within 10-15 seconds. And if your sunburned retina is not very sunburned, all it does is for the next couple of days until the sunburn goes away, it feels like having sand in your eyeballs. You can't get rid of it. Okay, that's what I've been told. I've never actually had it. I tend to use safety glasses, goggles, or a welding helmet. But if you do it long enough, you'll burn your retina and you'll go blind. How about that? Even better, right? So anyway, we've got the coating here, and the coating comes in various types. We call them, this is a basic coating. It has a little number on the side. It says 7018. Can you see that? Yeah, there's a 7018 in ink on this thing. Here's a 6011. Okay. Hopefully we can see the 6011 there. Okay. I think I have a 7014 here. Anyway, I'll pass some of these around, and you can see different electrodes. Actually, I'll keep 2 of them, plus 2 others. So here's 3 different types of welding electrodes. There are dozens of types of steel electrodes for different steels. The 6011s, the 60 means 60 KSI strength. The 11 is the type of coating and the type of polarity, AC, DC, positive or DC negative from your power source. And this is a cellulosic coating, and I should be able to bend it about 90, well, not quite 90 degrees before it starts to flake off. Okay? So the coating flakes off depending on how freshly made it is. If it's freshly made, it's kind of rubbery, I can often get nearly 90 degrees before it starts breaking off. If I take a 7018, now unfortunately these 7018s, these were baked at about 400 degrees Fahrenheit to get rid of most of the moisture. These were baked at a higher temperature, but these have been sitting around in the air. And this one, well, I got about 15 degrees before it started flaking off. Okay? And that's because it's basically a brittle, glassy coating. It worked better this time, didn't it, Jordan? Okay, I showed this to her a couple of weeks ago. But in any case, the 7018 is baked at around 400. This one's baked about 750. There's less moisture in the 7018. The 7018 is known as a low hydrogen electrode. The 6011 is a normal electrode, or high hydrogen. We don't usually call it high hydrogen. We call the ones that are low hydrogen, low hydrogen. Okay, so in any case, we have different types of electrodes because that controls part of the moisture. Yes? Well, first of all, they have a 1-year lifetime. Okay, if you let them sit around for 10 years, they will pick up moisture from the air in New England. In Arizona, not so much, but in New England, they will pick up moisture from the air. And typically, the 7018s have to be kept in a rod oven at about 200 degrees or 250 degrees Fahrenheit and used, if you're dealing with a high-strength steel, sometimes used within 1 hour of taking them out of the oven, because they'll start to pick up moisture right away. And it's a question of how much moisture. I'll get into how much moisture, but I think your question is how long can I leave them out? Cellulosic electrodes you can leave out for a year, because we didn't try to drive the hydrogen off. The arc for a cellulosic electrode is 60% hydrogen. You're burning off the cellulose and creating hydrogen. We're actually using hydrogen. The cellulosic electrode came from wrapping paper around an electrode in 1910. And they found, oh, they got rid of the nitrogen porosity in the steel. They didn't know it was nitrogen porosity, but that's what happened. By burning paper and creating a H2H monatomic hydrogen, CO, CO2 plasma, they excluded all the nitrogen in the air. They got a good weld. A guy in Göteborg, Sweden, found sticking his bare electrode in the mud at about 1910 and welding with a muddy electrode excluded all the porosity that came from welding in the air, in terms of the nitrogen in the air causing porosity. I go through this in my fusion welding class, okay, in a little more detail. But anyway, that in Göteborg, Sweden, that became the beginning of what's now known as the ESAB company, which is one of the world's largest welding companies. But they learned to use muddy electrodes. They were basically using minerals from the mud, okay? But they had a lot of moisture. But then we learned in the 1940s, when we were doing welding of ships for World War II, we learned you need to dry out these electrodes by keeping them warm. You go down here to New London, or Groton, Connecticut, where they're building nuclear submarines, they will issue you a dozen electrodes or 20 electrodes at a time. And you have to bring back the stubs to prove that you used up all 20 of them. And they don't want you carrying around these electrodes for more than 2 hours at a time. And you may have an insulated little canister that you hold them in to keep them warm and keep the moisture off. Yep. Yeah. Yeah, and if you're using if you're using mild steel, as you brought up the term the other day, mild steel, it's almost impossible to crack mild steel. It's got such a low stress. The residual stresses from a low strength steel are so low, that circle is so small that you got to really work. I tried to do it in the laboratory once and I couldn't get it done in a week, okay, with a number of different things. It's the high strength steels, the things we use for nuclear submarines, for bridges when we want to save weight and we're using 100 KSI steel. If you're trying, you never would weld on an aircraft landing gear, okay? Forbidden. 250 KSI steel, I mean, you got a huge stress circle there. The only thing you can do is get rid of the other two things, okay? So it's a question of, you got to get rid of at least one of these, and the higher the strength of the steel, the more you have to be careful about maybe working on several of your approaches to avoiding hydrogen cracking. Mild steel, not a big problem. You can use cellulosic electrodes. You're welding a regular old pipeline, root pass goes in as 6011, cap passes go in as 7018, because I didn't tell you, but you can pass them around again if you want. Those were the same diameter of steel rod, but the 7018 was much thicker on the flux. That's because it contains iron powder in the flux, and it gives you a higher deposition rate. Okay, you can weld faster with 7018 than 6011. The type of weld, you're not welding on something fancy, right? Yep. Yeah, well, these excavators, a lot of them are using 100 KSI strength material, and stupid, if you don't kind of control your hydrogen on high strength steel, and I've seen people lose their lives because of it. There's a lot of, I call it farmer welding. I once estimated, 30 years ago, I was trying to figure out how many welders are in the country. I asked myself, how many welders are there in the country? So I did an estimate. This is actually a story, another story. I'm never going to get to welding. But So I wanted to know how many welders. So I said, well, I knew at that time 60% of all the welding was done with stick electrodes. I knew how many pounds of these electrodes were sold each year. I knew how many pounds per hour a welder could put down. You put all this together, and I calculated in order to burn up all those millions of pounds of electrodes, you needed 700,000 welders in the United States. I thought, well, but not everybody's a full-time welder. Let's assume that 500,000 are full-time welders. Even a full-time welder may only be welding half the time. He's out doing something else for part of the time. And then a lot of them are auto mechanics, farmers, whatever. And so I estimated there were 500,000, if I calculated 700,000 full-time welders, then maybe there were 500,000 people who would consider themselves a full-time welder, whether they welded 40 hours a week or 20 hours a week, and another 1.5 million who were part-time welders. You're a part-time welder, okay? You've welded before. That makes you a part-time welder, right? And so, okay, so I go to some welding conference and I say this just to give some people some perspective, and because I couldn't find it in the literature. And I think the 8th edition of the welding handbook comes out about early 1990s, and I'm flipping through it when I get my copy, and I see right there near the introduction it says there are about 2 million welders in the United States, and or something. I thought that's the same number I got. But it had, the reference was the Bureau of Labor Statistics. And I thought, okay, so I called American Welding Society and said, what's the reference to the Bureau of Labor Statistics that has this number? They said, oh, they called us up and wanted a number, how many welders, so we gave them your number. So, okay, at least I knew how it was calculated. Okay, Bureau of Labor Statistics didn't know how it was calculated, and they were using it, but I knew how it was calculated because I did it. That's one of a couple of times where I made some estimate and all of a sudden it became the gospel truth in the world. But actually the other time is, how much does it cost to build a steel plant? What happened was my oldest daughter was working for Clayton Christensen one summer when he was writing his book, The Innovator's Dilemma. And she came home and said, she was in college, it was a summer job, and she said, Dad, Clayton wants to know how much it costs to build an integrated steel plant. And I can't find that anywhere in the literature. I said, and you won't, Rebecca, because no one's built one except a country, okay, since, I told you that story yesterday. And I said, however, I have a slide that I used, and I'll bring you a copy of it. So this slide was put together in the, it's a little airport in northern Michigan. I was sitting there with a graduate student, and we just visited General Motors. And we were talking about steel plants, and I just sketched out, this is what a mini mill would cost approximately, this is what, and I had $15 billion for an integrated steel plant. So I gave Rebecca my slide, and I'm referenced in Clayton Christensen's book. Okay, we just pulled it out of the air at an airport in, I can't remember the town, I'd have to look on a map, of Saginaw, Michigan. I was in Saginaw, Michigan, sitting in an airport, nothing else to do. I came up with a number, okay? And there it is. The rest of the world now knows it costs $15 billion. They haven't got a clue where the number comes from, but they will all reference it, okay? There actually is a basis for my pulling out these numbers, but anyway, just pull the number out, okay? There's probably a few others I don't even know about. Okay, just tells you about scientific rigor, okay? Anyway, did you have another question? Okay. Well, anyway, these little stories keep life going here. So moisture, humidity. You're not supposed to weld, according to the U.S. Navy, you're not supposed to weld a nuclear submarine if it's more than 85% relative humidity. Do you know how many days in a shipyard right next to the ocean on the east coast of the United States, which is where we build submarines, either in Newport News or in Groton, Connecticut, it's above 85% relative humidity? About 200 days of the year, it's above 85% relative humidity down there next to the water, right? It's not too surprising. So do they quit welding for 200 days a year? No. They keep welding, okay? They're supposed to be controlling the hydrogen by keeping the moisture out, but in fact they do a few other things over here on these other circles, and so they don't have big cracking problems. But they did When they went to build some of the mock-ups for the Nautilus submarine in the mid-1950s, which was the first nuclear sub, before that they just used low-strength steel. So the other night, Run Silent, Run Deep was on or something, and the Olympics hadn't come on, so I just put on this old Clark Cable, Burt Lancaster movie. And that submarine, when they dive deep, they go to 200 feet, okay? Because they just use regular old low-strength, mild steel, whatever you want to call it, for for submarines in World War II. For nuclear submarines, when they came up with the Nautilus, they were using HY80, which is that piece I passed around. 80 KSI as opposed to 35 or 40 KSI. And so they could dive deeper. I won't tell you how much deeper because it's classified, but it's a lot more than 200. It is more than double 200 because they did other things on the design and fracture mechanics and other stuff. They can go a lot deeper than 200 feet, okay? But I can't tell you how deep. In any case, when they first started welding, some of these egg crate type of construction, you know, all these stiffeners and stuff in the submarine, they'd weld it up during the day, all kinds of residual stresses, so the big circle there. They didn't have very good hydrogen control on their electrodes. They didn't check them out back in 1955, where you could only have them out of the oven for 2 hours, and you had to bring back a stub for every electrode you got. You had to bring back a stub, and there's some little clerk there counting your stubs before you can get more electrodes and stuff. They didn't have all these hydrogen controls, and so some guy welding at night would hear this piece that had been welded during the day, and it'd be a big boom like a rifle shot. Okay, a hydrogen crack just ran through the part they had made that day, 8 hours earlier. Delayed cracking. The hydrogen diffused to the crack tip during those 8 hours. Now, what do? They had to keep building some of these things, so they used austenitic stainless steel. Austenitic stainless steel has a face-centered cubic structure. There's lots of room for the hydrogen in a face-centered cubic structure as opposed to a body-centered cubic structure. The cracking susceptibility of austenitic stainless steels is much, much less than body-centered cubic steels. And so, just to get some of their work done, they welded some of for their structures and stuff. They ended up welding with austenitic electrodes before they finally learned how to do it successfully in the steels with ferritic weld metal of matching strength. The problem with the austenitics, you wouldn't get the same strength. So here is the iron-hydrogen phase diagram, and we'll come up with some numbers here of how much hydrogen will be in the steel. The problem is, and I've done the 1 atmosphere curve. This is a plot from Carl Zaffe, who was a hydrogen cracking expert 50, 60 years, 70 years ago. 1/10 of an atmosphere, 1 atmosphere of hydrogen, 10 atmospheres, 100 atmospheres of hydrogen. As a function of temperature, here's the melting point of iron. And above the melting point, you can dissolve, I'll come down here, it says cubic centimeters of hydrogen per 100 grams of iron. Well, that's within 10%, that's parts per million atomic, okay? Or parts per million by weight, I think, yeah, by weight. Relative volumes of hydrogen, atomic percentage, but if we're interested in weight percentage, that's 30 ppm. So at the melting point at 1 atmosphere hydrogen atmosphere, the equilibrium is 30 parts per million hydrogen, or cubic centimeters per 100 grams of iron. That's just because that's the way you measure it. You basically put your sample into a little chamber and you measure how much hydrogen, how many cubic centimeters come out of the specimen after you heat it up inside this closed chamber. At the melting point, it rejects hydrogen down to less than about 5 or 6. And then you get down here to where the delta iron transforms to gamma iron, and you see the higher solubility of hydrogen in austenitic steels. And then you transform at 910 to BCC again, and you see that the solubility goes down to something on the order of 1 part per million. Okay, so that's why the hydrogen's there. My secretary will send you, if she hasn't already, a little video that was done by what used to be the Norska Veritas, is DNV now, and they used to classify ships. Now they do all kinds of metallurgical consulting around the world for big oil companies and people. And so they have a nice little video on hydrogen cracking. And it's about an 8-minute video. I watched it for the first time this morning. You ought to watch it. It's gonna show you some of the same things I'm telling you. But it's got some videos where they weld on a piece of steel, stick it in glycerin, and then they take a video of the hydrogen bubbles coming out. You can see them in the glycerin. If you do it in water, it would be coming out like my Sprite, right? All in one big foam. You do it in glycerin, because of the viscosity of the glycerin, you can actually see the hydrogen coming out. And it's a lot. Believe me, it's worth watching this. Well, I don't know. You may not think it's worth watching. It's a homework set, so you can decide whether to do your homework. So I'll send you that. But it's going to talk about hydrogen cracking in general. Okay. There's also another one I'll probably send you that some people in the Netherlands did in the 1950s with similar types of tests. And then I was looking for one that had been done at RPI, a video. I didn't find that one on YouTube. But in any case, if you look there are books, whole books written on hydrogen cracking in steels. I must have one here somewhere. Okay, so this is the second edition from the British Welding Institute. Welding steels without hydrogen cracking, and there's all kinds of authors. Frank Coe wrote the first edition by himself, but he had lots of help with the other editions. And in that book, there is this plot, which was in Coe's first edition. So Frank Coe put this together. Very intelligent man, as opposed to a lot of his co-authors for the second edition. Okay, weld hydrogen level, milliliters per 100 grams of deposit. That's the same as cubic centimeters. So you can think of this as parts per million. And you can have